Fernando. Lewis. Jordy. Gabriel. Yeah. Corinne. I don't know if she's coming. Soraya. Yeah. Soraya.
Yes, thank you.
Aaron. Kate, or I guess Aaron Gillespie. Aaron, right? Okay. But E? Yeah. Zachary. Samantha. Alberto. Alberto. Andrew. Stephanie. Brooke. Aaron Sabalos. You have no. Alejandra. Rodrigo. Okay. Yella. Alexander. Madrigal. Oh, Jake. Abraham. Oh, perfect. Edsel. Let's put homeworks here. Okay. Veronica. Adam. Estella. Jasmine. Kevin. Mendez. Ashlyn.
Yeah.
Roach. Giselle. Wait. Angela. Valeria. Daniel Garcia.
No, it's classic. I don't know if it's called that.
Wait. Oh, Tessie. What? Oh, right on top. Edgar. Ashley. Alejandra. Omar. Axel. Casey. Kyle. What do you look for? Axel. Diana Morales. Haley Scott. All right. That works.
Well, for all. Yeah.
That's not mine. Okay.
Thank you. Hello.
Oh, hi. Yeah. Okay, sorry. I'll look for it. What was your name? Yeah, but if I have it, then it's probably graded. I just lost it.
Okay.
Are you on Slack? Can you send me a message that just has your name and is like, yeah, I did find it. Out? Yeah.
Oh.
Are you playing with what? Nope. Out. You bring that in? Homework's there. This is wrong. That's right. In third place. Homework there. Yeah. And then
See this homework form is the guy.
but then I guess. Okay, I'll send me a message to double check. Homework goes there. Checkup's here. Okay, folks, how's everyone doing? Medium. Okay. My personal depression has been averted until Friday. Find out whether or not Dodgers get eliminated. But then you don't see me. So I probably will be okay on Tuesday. And if they win, then I'll probably go to the game on Monday. And then I'll probably be unokay on Tuesday. But you won't be able to tell. Yeah, sorry, homework 6 in the box. Check-ins if you haven't gotten them here. If you've read your score on Canvas and you don't know how to interpret it, it's here. Okay. This is kind of stupid, in my opinion, because like, what's the difference? Right? That doesn't mean anything to me. 0 means I didn't get anything, I guess, all semester. And like D- is like what? Just rude? I don't know. So this is passing D, 1 point. Okay. So far, there are 2 groups of people. There are the people who turned stuff in and the people who didn't. So we're going to talk about that. I am under no legal obligation to fail any of you, just so you know. So I would prefer not to. I did post slides today, and I posted the old ones. Sorry about that last time. Folks know what these are? Atoms, right? Okay. We're going to talk about light. Hopefully we'll get to atoms today. If we don't, I'll just adapt the slides. If we make a ton of progress and we just breeze through the atoms really quickly, we'll talk about atmosphere. But that seems unlikely. So when you go and you look at the slides today and you see there's 47 of them, don't stress. We're not going to get through all of them. Okay? All right, that's the distribution of grades in the class. What do you notice? A lot of A's. You see that I'm not afraid to give an A out. You make an argument that you deserve an A. I agree with you, you get the A. Is that contractually binding? No. Can I change my mind? Yes. If you are here, does that mean that the semester's over and you'll never recover? No, don't. No. It means that I like trajectory as much as I like results. So if I'd say in the first check-in, or you say in the first check-in, man, I could really improve my homework scores just by writing a bit more. And I'm like, you're right. I agree. You get a C here, but if you do better and you improve the homework that you've done, this could be an A. Right? So these are check-ins. These are showing you where I think your grade is currently, but not like, oh, take A plus A plus A, and then you get an A. These will be cumulative for the entire semester. So at every check-in, you will turn in all homework and all revision. Does that make sense? So keep your check-ins, don't throw them away. Because if I tell you to do something, and then the second check-in you didn't do it, you're like, what the hell? Okay? Cool. Is your name on this list? You don't have to raise your hand if it is. If your name's on this list, one of three things is true. You don't have a check-in score. Okay? That's either because you didn't give yourself a grade, and I want to know what you think your performance is so far. It's because I need something from you, or it's because I didn't get it. So there's a lot of names on here, and that will fill in the rest of the scores, right? But if your name's on there and you think you turned your score in or you're checking in and you also like gave yourself a grade and you don't know what's going on, let me know. Because you can't pass the class without turning check-ins in. That make sense? Okay. Here's what I saw, some major themes so far. So in the homework, I think there's a miscommunication on my part as to what I use confidence for. I use confidence to understand how you're feeling about the answer. If you're very confident in it and then you get it wrong, that tells me that it's a misconception, something that you feel very good about, but that maybe wasn't explained properly. As opposed to if you don't feel very good about it and you get it wrong, that's okay, right? Like that's me saying, oh, they're at least assessing their own understanding here. And then from there, being able to expand my, like come back to that concept and work on it a bit more, right? So that's the confidence. It does not affect your grade. So people are, putting in the check-in like, oh, I thought my confidence scores brought my work from an A down to a B. Like, no, if you did it and you got the answers right, but you weren't confident, that's even better, right? Because then that means that you still tried, even though you weren't super confident in your answer. Lecture tutorials can be finished out of class. So don't give yourself minus points for finishing that out of class. Also, don't not do them just because you couldn't be here that day. If you can grab them online and you do them yourself or you do them with a friend, that's great. You won't see them, but I see them. When I get them all back, I go through them. I find out what people had the most trouble in, and then I make it a homework problem. Right? It's a communication. All of the assessment is you communicating your understanding to me. It's not, I know that I do tricks and quizzes and shit. But the goal here is for me to understand what you understand. That's my responsibility. Similarly, I expect that clicker questions will be wrong, right? That's how you test your knowledge Like, I'm pretty sure it's A. Oh shit, I didn't know what I thought I did, right? Or I'm pretty sure it's D. Oh, I am right. Okay, I wasn't super confident, but at least I stuck myself out there, right? Similarly, I don't need a good excuse for how much to be late. Okay? Everyone's gonna have different reasons. For someone, you might think to yourself, oh, it's just a blown tire, like I should have turned it in, like I had an opportunity to do that. You keep sort of like ranking where your excuse is and the goodness will never win. Someone always has a better excuse than you. So I'm not gonna be the metric of like, that's a good excuse, you can turn it in late. What I want is personal accountability. You're on track, you're gonna do it. Ahead of time, I'm telling you, it's not ready yet, I need another day. Or I need 2 days, or I need 3 days for the weekend, right? That's accountability in accepting late homeworks. Is that fair? Okay. If you turn in homework late and it's excused, does that count against you? If it's excused, it's fine. It's the same as turning it in on time. Okay? I care that the work gets done. I don't want it to all happen at the end, obviously. Questions about any of this? Should I have taken anything else away that I didn't? Okay, no one screamed at me in the check-in, just fine. You could do that too. Remember that there's an anonymous issue form. If you didn't feel like putting your name to a complaint, you can complain at me there. Okay, yeah.
That it's gonna be late, and we have to let you know and take care of the day after.
So, sometimes you walk up to the front and be like, oh shit, I forgot to print it. That's fine. Same day at class, beginning of class, fine. End of the day, after class, not fine. Okay. Cool. Let's clarify one more thing. We're talking about tidal heating. Just some of the feedback that I've been seeing in the homework and from conversations. So in the inner solar system, when it's a rocky body, we discussed the 3 forms of heating. First, you have accretion. That's where you add material in the process of making a planet. And then differentiation. That's when heavy stuff sinks and light stuff floats. And that is an energy source. So as that stuff sinks, it provides heat. And finally, radioactive decay, which is the dominant form of heating in the interior of our planet today. And that's from the decay of uranium and plutonium, right? So that's in the inner solar system for terrestrial bodies, for stuff that's rocky. And then we sort of branched past that. We talked about tidal heating, which is much more important when you have an icy body. So any moon of a giant planet, or for example, Pluto. And in these cases, tidal heating works best, but is not restricted to these conditions. So if you have an orbit that is eccentric, one that gets closer and farther to the parent body, right, like a squish circle, great. If you're very close to that parent body so that the force of gravity is strong, great. If you're in resonance, that means that you go around for a multiple of whatever this other person goes around. So for example, if I go around twice for every time that my nearest neighbor goes around once, that means that just like when I'm pushing on the swing, it's the forcing at exactly the same time, and those forces can build up and make the impact stronger. So if you're in a resonance, that helps, but not a requirement. Being in an eccentric orbit, not a requirement. You could have like 2 of these, or you could have 2 of these, or you could have this one and that one. If you have all of them, wonderful. That's how you get Io, right? Io is eccentric. It's really close to Jupiter. It's in resonance with its nearest neighbor, Europa. Its surface is icy, and its parent body is one of the largest in the solar system. So it is continuously volcanic for 4.5 billion years, right? Is that a good clarification, or did everyone know? Yeah.
Is it cryovolcanic or just normal?
Normal volcanic. This is real volcanic. There are certain places, of course, where cryovolcanism is all you can get away with. The question here is there enough tidal heating to deform ice, or can you deform rock? And in a place where you only have cryovolcanism is a place where you don't have enough heating to melt stone, but you do have enough to melt ice. Right? Okay, we were learning about something. We were learning about the colors of things and how this is related to temperature. And we were talking about things like an iron poker in the fire and how it'll glow. And that will tell us about the temperature. I talked a little bit about the fact that a human being emits light that is in the infrared. So we can think of this as the visible. We can think of anything on the purple side as ultraviolet in this region. And then other stuff out here. This will be the red, this will be the infrared, and that's where humans are, right? Okay. Let's get our brains going. We're gonna do a clicker question. You don't have to know this, that doesn't important. Okay. So these three curves show the total energy here on the horizontal or the vertical versus wavelength. And for folks who can't read this, this is the ultraviolet, visible, indigo, blue, green, yellow, orange, red, infrared. So the same way that we just had it before. Ultraviolet over here, infrared over here, visible right in the middle. Okay. Which of these objects has the highest temperature? Okay, interesting. Interesting. Everyone done voting who wants to vote? Okay, we have a 3-horse race, which is great because there's only 3 answers. Why don't we take like 2 minutes, ask your nearest neighbor who disagrees with you what their reasoning is. Okay?
Yeah.
All right, let's try it again. Buzz in when you're ready. That everyone who wanted to buzz in? Like 15 less people. Okay, I'm gonna leave it open. That changed basically no one's mind. So a lot of people like A, equal number of people like B and C. There's a slight preference for A. Does anyone want to like talk through this? Aaron. Oh, interesting. Okay. So we're just talking about hot right now. Okay, not total energy. So you just looked at what? The colors. And you looked at this line, you saw this is where it peaks. And we talked about before the idea of like where it peaking is like the color we assign to it. And so you said this is the one that's most in that direction. So A would be what color? Green. C would be orangey yellow, right? I don't know my colors good, so you'll excuse me. And this one is like between violet and ultraviolet. Yeah.
I chose A because there's more of everything in that what I think is releasing a lot more energy, so overall, it's just harder to give more of everything.
Yeah, right. So that's a perfectly good way of thinking about this. If we had some understanding of what this bar meant. So the only reason why I'm using this one here is that this is sort of an arbitrary unit, and we're trying to connect to this idea between how hot something is and the temperature at which it peaks, or the color at which it peaks, right? So for example, you could have a bigger object put out more energy than a smaller object, but the smaller object is hotter. Does that make sense? Yeah, okay. Yeah. Oh, okay.
I do explain it, I was like, oh, yeah.
Yeah.
A bigger sun does not mean a hotter sun.
A bigger sun does not mean a hotter sun. So we can get really hot fires as long as they're small, right? Yeah.
I chose B because like on the electrical tutorial and like in the slides last week, the farther along something was up to the left, the waves were shorter. Which meant that there was like more, like, we got the energy stronger and more than.
Right. Yeah. So that
The longer.
we looked at the waves in the electromagnetic spectrum, and when they were more compressed, they were more in the ultraviolet side, right? Good. Okay, speaking of lecture tutorial, how far did people get? Raise your hand if you finished it, even though I said don't finish it. Oh, good. Awesome. Raise your hand if you got through page 1. Okay, keep your hand up if you got through page 2. Oh, okay. All right, that's good. That's good. I want to get through probably 2 through yeah, I probably want to finish it right now. Is that okay? Okay, and then we'll talk about light as an information carrier. And the motivation here is this. So when we look around in the solar system, when we look around in the universe, the primary means of understanding the universe is through light. So I want to describe to you how we can possibly know things about other stars, how we can possibly know things about places that we haven't stepped foot on. And generally speaking, we're going to use information about light to understand composition. What is it made of? Understand how hot it is. And interestingly enough, whether or not it's coming at you or going away from you. All of these things are interesting for different reasons. This one may be the most, right? If you like planetary science. Okay. So this will get into some understanding of what's up with these little things coming up. Why are these things going down? We'll talk about that. We'll talk about what this little hump is, what this hump is. What color would you say this object is right here? Green? Is that right? Limey. Limey. Yeah, there's not a lot of blue, right? Okay, and like some little bit of red, little bit of greeny orange. Okay. All right, so if you're next to your partner, hopefully there won't be too much moving around. If you're not next to your partner from Tuesday, I guess get up for a second. If you weren't here and you need a lecture tutorial, let me know. Okay. Okay. Raise your hand. Good. Okay. Do you want to move around a little bit so it goes picture? Yeah. Just note where you had worked yesterday. Anyone else need one? Does anyone need a partner? Regroup, like to break up. You guys wanna? Hear you? I also have plenty.
So.
What color of light? I don't know, so for example, better, so which one is the red? Which one is the more red light could be a more thing now, it's like.
Like, we like.
Yeah.
Yeah. This one's more red. But.
Yeah.
I know, like, No, it's 100% free. We'll talk about it at the end. Yeah, right? They don't pay me.
We're not sure. Oh. So.
I know the class ain't that fun.
Yeah, we're trying to look up. Oh, we gotta go now. So there's not more of it. Thank you. It's really correct. Use of the word must be. Yeah, yeah. It's almost like it's so everyone they heard that.
Is anyone else in partner? Were you drunk yet?
Yeah. I was like, wait, I was thinking- Yeah.
Yeah. I don't listen to any science podcast. Sorry about that, though. James is asking about this in the Slack. So I don't know if you have an astronomy podcast you like.
That's also has one that was really interesting.
Oh, I think I did this.
Yeah.
Yeah.
Okay, how close to being done are we? Done? Raise your hand if you're done. Okay, raise your hand if you're like 5 minutes from being done. Okay, that'll work. So what about? Yeah. Did anyone get stumped on this? I don't get that.
Which was it? The trouble with the other one? Always. Oh, no.
You got time. You got time.
I'll go do that.
Like, you- Okay. Onward, upward. Okay. We're gonna talk about light. We're gonna learn about atoms, not for too long. I promise it's kind of interesting. Okay. So first things first, we're gonna describe a couple spectrum. So remember that we take a prism, we break light up into its colors. The first one that I want to tell you about is continuous. This happens when stuff is hot. So when stuff is hot, like the sun, you get all of the colors. Something's hot, you use a prism, you get the rainbow. Cool, right? Okay. Anything that's hot, sometimes dense liquids will do this. This is where you got that word from your lecture tutorial. Black body radiation. Radiation being light that comes off of something. Yeah. I've never seen that, but that's interesting. That's probably an atmospheric effect, like a rainbow. So the reason that a rainbow happens is because the water droplet is spherical and it acts like a prism. So the only way for you to see a rainbow is for the sun to be behind you and the water to be in front of you.
Like the metal itself.
Yeah, so maybe the metal, I don't know. We'll have to think about this one. That would be like a prism inside of the, are you talking about like with welding? Okay, we'll talk about this afterwards. It's an interesting idea. I'll find out what that is. Okay, so this is black body radiation. This is a simplified way of thinking about matter, that if you heat up any matter, it emits radiation. And remember, radiation is light escaping. It's a cooling process. Okay, so this is the continuous radiation or the thermal radiation, same type that you get from your body being warm. This is what the snake is detecting so that it can bite you in your sleep, right? Okay. All right. There's 3 of them. We're going to talk about a few of them today. This is the one I just told you about. This one is those pokey lines that go up. In the thing that I showed you, the spectrum that I showed you, remember I showed you these pokey lines that go up and there's stuff that goes down. And if you recall from Tuesday's lecture, that kind of looks a little familiar, right? That's what? So this is sort of similar to the very first slide that I showed on Tuesday, which was the sun, right? We're going to see why that is. Okay, first we have to review atoms. Oh, no one groaned? I was really expecting everyone to hate that. What's an atom? The building block of matter. Okay. It's not mitochondria, right? What's it? Smallest unit that you can measure physically, is that right? Okay, all right, that's pretty close, pretty close. So no one here subscribes to the idea of continuous media. You all believe this fake news that like material, everything that I touch is little dots and there's space in between? That's crazy. What? You're telling me the whole universe, when I sit on this chair, why don't I just go right through it? The what?
Yes, I like it.
All right. If I were small, I could fall through things, right? Okay. I'm very big. Don't comment. I'm 10 to the 26th big, right? You realize avocado's number, which is like how many atoms are in a mole. Okay, so what is an atom? It's that thing we showed at the beginning. This is a sketch. This is not accurate. So you think about it like it's a sun and there's a planet going around it. This is wrong, but it's helpful for us to understand. Okay, these are the so-called building blocks of everything that we see. And inside of here, there are smaller building blocks. But you won't learn about those, and don't let people learn you about those. Okay, weird. The simple ones, like hydrogen, are composed of something like a proton. And the proton has positive charge. And the electron that goes around it is this color for some reason. And it has a negative charge. And they are attracted to each other by electromagnetic attraction. But they don't just fall into one another, because the electron can only live in certain states. And this is really important. So currently I can walk around most of this floor, right? And I can stop anywhere I want, and I can keep going anywhere I want. The electron is not allowed to do that. The electron can be here, or here, or here, or here, or here. But it couldn't have been in between. Does that make sense? It shouldn't make sense anyway. Why are you're nodding like it makes sense? This is a very strange thing for things to do. If I threw a ball and it wasn't allowed to move along the way, it just could be here, here, or here, you'd be like, that's fucking weird, right? But that's what electrons do. Electrons do not have continuous energy. We talked about the continuous spectrum, right? So we're going to relate this idea of how light interacts with matter, and in particular, how each one of those steps took energy for me to go up, right? In order to climb those steps, I had to like exert, and then I would come back down and I got it back. I didn't really get it, but you get it, right? Okay, so that's the basis. That's how we think about these steps in an atom, layers in an atom, and the electron is going to do all the climbing. It's going to go up the steps and it's going to go down the steps. Oxygen atoms, they're more fun. They have more steps. They have more electrons. They can do more fun things. Molecules get to do even more fun things. So chemists tell me that there is something that goes on with these two. They're like friends, they're bonded. And hydrogen has an electron and oxygen has electrons, but like they're friendly or something. Okay. And then oxygen can make your burrito warm, right? How's that? Yeah, what makes the water in your burrito warm? Microwave, right? This is the canonical. I told people that I wasn't going to do more food analogies, and I lied. Right away, I lied. Okay, so here's the idea. You get water to start moving. And because water, see how it's configured there? Each one of the hydrogens can move away like this. in both directions. They can move together. They can move like that. They can also rotate. And they can spin, right? They have all these degrees of freedom that allow them to heat up nearby molecules. And they're really good at absorbing microwaves. They love it. They go, whee, get really excited. Okay. So they absorb the microwave and it makes them energetic. Right? So just think of that. Microwaves is like getting sugar to a child. Okay. Again, food. Here is a molecule. The things inside of it are atoms. Each atom has different numbers of layers, different numbers of steps. Okay. And we can tell the difference because each one of these steps is at a specific location for a specific atom. So if I take a gas, an unknown gas in some tube, and I take a prism, and I'm very careful, and I mark down where I see all of the light from that gas, I can tell you what's in it. So up here, this is carbon. This one's better. Okay, over here, purple, good. I'm good with colors like that. Red, good. Carbon, it's got some steps in it. Here's some steps here, steps here, steps here. And nitrogen looks a little bit more complex, right? What's the atomic weight of carbon? Does anyone know?
Spider, right? Well,
12, is that right?
oh, it's right there.
What is it? Let's see. Yeah, it's right here. It's 12.00011, right? Okay. What's nitrogen? Don't read it off the thing. Right next to it. You already read it? What? 14? What's oxygen? 16, very good. What is neon? Neon's over here on its own, right? A noble gas. Says, I don't want to participate in any chemistry. Just use me in lamps only. And here's why neon lamps look the way they do. What color is a neon lamp? What? Neon. Incorrect, not a color. What? Yeah, it's like yellow, red, right? Like, see these colors over here? If you see a pink neon light, is that neon? No, you've bought a different gas. Okay? Neon only gives off one color. Okay? What's magnesium? Magnesium's 24 over here. Okay? And neon has a lot of steps. Electrons like going up and down these steps. Magnesium seems to be doing something strange. Okay? What I want to draw your attention to is these two lines right here. Anytime you have these two lines sitting right next to each other, they're sometimes called a doublet. So we might see this again, say, in the sun, where there's magnesium. You'll see this exact feature in the red. Right? See this double in the red? Hold that in your mind. Okay. Here's some more examples. Here's hydrogen. Real boring. Right? Hydrogen's got one step, and then another step, and another step, and these other steps. Let me ask you a question really quickly. If we thought about the steps as color, right? Like this is red, and this is blue. Which of these two has more energy? Same or not the same? Raise your hand for same. Okay. Raise your hand for red, has more energy. Raise your hand for blue, has more energy. Raise your hand for, I thought we were going to raise our hand and we're going to do quicker. Okay, good. I love that honesty. Okay, good. So let's go back to this idea that we had on Tuesday, which was the idea that the wavelength of light, or I should say the color of light, tells you about the energy. And that blue light was more energetic than red light. Similarly to what we just did in the lecture tutorial, where if you see something that is mostly red, hot, probably hotter than something that's, or sorry, less hot than something that's blue. Okay? Or lighter. Okay. So what we can do when we see something like this is we can interpret these as steps. This is a step. Let's say it's like up to here. This is a bigger step. Bluer step, larger step. Any thoughts? If I don't have a food analogy, you're never gonna get it. Okay, here's neon again. Those are some of our favorite colors. Only thing that happened in this picture is that we flipped it. In the last one, we had red on the right-hand side. Right, so I just flipped it here because I don't know why I did that. All right. Here's an example of how we use this in nature. This is the Crab Nebula. We talked about this at the beginning of the semester. So this is a supernova remnant. What happened is in 1054 AD, Chinese astronomers looked up and they said, that star wasn't there yesterday. And it wasn't. They wrote it down exactly where it was. And a couple weeks later, star disappeared. Like, that was fucking weird. But they kept really detailed notes about where it was in the sky. And so we went and we looked with telescopes and we saw this cool thing. It's like pretty cool. And in the very middle of it is a dead star. And that is its exploded guts. Okay. And we can find out what the exploded guts are made of because we know, for example, what the lines of hydrogen or the colors of hydrogen appear as. So if I take the light from, if I take, say, a little sample of light right here, and I use a prism just on that tiny piece, I can say, what are you made of? I break it apart into its colors, and I can see whether or not there's lines. And if those lines match up, like here, see there's oxygen. I know an oxygen is supposed to be there. That's a line that comes from neon. That's a line that comes from hydrogen and hydrogen. And there's another one over here. That's oxygen. Oop. So in this gas cloud, I can see hydrogen, neon, oxygen. Right? Cool. This is called an emission spectrum. It emits. It's bright on its own. It's hot, but only at these very specific locations. And it's dark otherwise. Right? Nothing. Come on. Okay. Good. Here's how it works. You have a cloud of gas. You break the light up. You see the lines. This is like a barcode that we can scan the universe with. Legitimately. Like this is like how people find out what's where. The word helium over here. Okay. He. Helium sounds like. Anyone know Greek or Latin? What's that? Helios. What's Helios? The sun. Yeah, God of the sun. Helios is the sun. Where did they find helium for the first time? In the sun. That's correct. They did not find it on Earth. They looked up at the sun and they were like, oh, there's all these weirdo lines up there that I've never seen on Earth before. There must be a unique element that only exists in stars called helium, named after the sun. Well, that's because helium's kind of a diva, right? The first diva of the noble gases does not participate in chemistry. So if it is in the atmosphere, it just leaks out. You put it in a container, you work really hard to put it in a container, and you wait like 10 years, and it just got out.
Like running out of helium.
Yeah, we run out of helium. Only places to make helium are nuclear reactors. You can trap it from inside the Earth, but that's problematic in other ways. Okay, so you get some that's trapped interior of the Earth, but if you just leave it alone, it just escapes. Doesn't care about any of your constraints. Okay? Not exactly. But yes, it's been a nuclear reactor. It's a byproduct of nuclear reactors. Because we're shutting down nuclear reactors because of people's, well, I'm not going into this. Yeah.
Are we into the business with?
So first thing, no dumb questions. There's no such thing as a dumb question. The only dumb question that exists is the one you didn't ask. Okay. Second thing, can you do this with people? Can you get the composition of people by a spectrum? Yes. So what you're looking for is, we do this on surfaces all the time. So we fly over a rock and we look down on it and we use not visible light, but the light that we emit in, which would be the infrared, right? And so you can tell, oh, there's like carbon in here, there's nitrogen in here. And depending on how big the molecule is, it might have a specific way that it interacts with light. And it's like, oh, that's a living thing. Right? Okay, good question. Next. Emission, this makes sense? Everyone's experts in emission? Okay. Now we get the opposite. Absorption. So if you squint, you can imagine each one of these fills in, right? Like just flip it over like it's teeth and then slide it in to this picture. Okay. This is called an absorption spectrum. So this is when you have a hot thing. And then you put gas in front of it. And the gas in front of it absorbs at the specific wavelengths according to what's in the gas. So if this is a gas cloud of hydrogen, then it only pulls out those few colors that we talked about earlier, and the rest gets through. The reason for that is the light is traveling. There are electrons in this cloud of whatever it is. And they are like, hey, I like that light. They grab it, they jump up a step, and they just stay up there. Okay? But they can only do that at the steps they're allowed to be at. They can't just do it everywhere, because they're those weird balls that don't exist all along the way. They only exist 1, 2. Okay? Yeah.
So say hypothetically, sun's sitting there and there's a cloud of elements in space and it happens to float in between us and the sun. So say we just one day lose green for a while, if it happens to be predominantly absorbing green.
So that's a good question. How big are these? Right? That's the trickiest part. Are these like huge sections of color? Or are these lines exaggerated? We'll show you this. Great question. Okay, so here it is. That's the sun. But remember the first day of class, and it was kind of like all stretched together. This one, I take all of it and I stack it on top of each other. So it starts over here in the infrared, gets redder, 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 redder. Then it finally gets into the oranges and the yellows and the greens and the blues and the purples. So if you notice here, the lines are small. They're really thin. So even if we have this thing that's really good at absorbing, say, a very specific color, you got all this other green to fill in, right? So in fact, by eye, you look at the sun and it looks white. You never know that it wasn't white. But when you take a prism of it and you take a spectrum of it and you look at all of the individual colors, there's a lot of places that are missing, right? How could that possibly be? The sun is very hot, so that's the continuous spectrum, hot source. What's the cold gas in between us? Space is no gas, right? Space is the absence of stuff. Which atmosphere? Yeah, so they both have atmospheres. The sun has an atmosphere, that's where we found helium. And we have an atmosphere, thankfully, that's what we're breathing, right? This one here does not have any signatures of the Earth's atmosphere. This is all stuff that exists in the sun's atmosphere. And the sun's atmosphere is a really wild place. Remember I told you that there are these two lines that are right next to each other in the red, right? They're here. So that means that there's magnesium in the atmosphere of the sun. Is that weird? Magnesium is a metal, right? You don't really think of it as a gas, but it can exist out in space. As long as it's hot enough, it won't condense into something. Okay. Okay, so let's have one look at this. What can this tell us? What types of things do you see? Raise your hand. Yeah. It's what? It's more red? Good. Okay. First one here, it's more red than blue. Good. First feature identified. Anything else? Yeah. There's stuff that goes up and stuff that goes in. Very good. Anything else?
There's a certain layer of infrared and then it spikes up again later on.
Yeah, it like goes down. That's weird, and then it goes back up. Very weird. Is that it?
I'm not sure if someone mentioned what's the energy level, right? You see that?
Yeah. We're looking here at the intensity. You could call that energy as well. How much energy you're getting from every piece of light, right? Okay, so let's see if we can understand what we're looking at. Okay, so if I draw this dotted line, this would be the contribution from the Earth. Oh. Right, I need coffee desperately. This is the contribution from the sun. Right? Why is it less? Someone new? Okay to be wrong. Both of the atmospheres, like, well, I haven't told you what this object is. We're gonna figure out what this object is, right? So if I tell you this is how much you get from the sun, why would there be less? Okay, I like that idea. Like maybe you're farther away. Not quite what I was looking for here. Yeah.
Something like pass through the object on its own.
Oh, like a transmission. We'll see a little bit of that, but not quite here. Anyone who hasn't spoken today, want to guess? Yeah.
Oh, would it be because it's being absorbed, you wouldn't see them?
Yeah, there's a difference between what's being absorbed and what's being emitted, right? So this is the emission from the sun, right? And then we can imagine this could be like filled in here, but this is missing. So what color would that be? What's that? Blue is missing. So what color would the object be? Red, right? We already said that, right? So the object is red, and this is the emission from the sun. Is this bouncing off of a red object? Some of it being absorbed and some of it being reflected? And maybe the reflection is not ideal because it's not a mirror. It absorbs some light, not some sunlight, right? Okay. See that? Is that unreasonable? You may or may not have to interpret an image like this. You will. Okay. What's this thing? No.
Oh, it's not on a planet.
No, I'm asking what is this? Let's not get ahead of ourselves yet. First, it's a red object, it's Mars. I mean, you're right, but let's not get there yet. What's this thing? The infrared light it emits?
Yeah.
What do you mean by that?
So like the infrared light, I mean, it emits its own light, so we can see it.
Right, remember we were talking about like what do snakes see? So snakes see that. That's the emission of light from the body itself. So this is stuff that bounces off of the surface from the sun. And this is stuff that comes from it directly. So if I look at the night side of the body, which of these two is present? This side? Or this side? Good. Okay, so the night side, you only see the infrared emission. Good. And the temperature corresponds to about 225 degrees Kelvin. You don't know what that is, but it's less than. Okay, so this object's colder than us. Okay. Now we have two other sets of features. We saw these ones here and these ones here. And you haven't memorized your spectral lines yet, right? In that 20 seconds, did you memorize them all? Okay. So these are actually absorption lines of CO2. And now it's really, we're giving it away. CO2, colder than us, red. Mars, yeah. Okay. So finally, there is an upper atmosphere. There's a hot layer of gas that's in the ultraviolet. That's up here. These are the emissions from Mars. Okay, fine. Y'all got it. It's too quick. All right. Before you leave, hold on. Don't go anywhere. So here are the questions that we want to ask coming up. We're going to talk about planetary atmospheres. One of the things that I think most folks talked about in their, like, what you want to learn about, was like life stuff. How full wide life? One of the major reasons is why did Earth's atmosphere end up so different from any of our nearby neighbors? We are the only atmosphere that has oxygen in it, right? All of the rest of it's carbon dioxide. Are humans capable of changing the planet? Yeah, unfortunately. Does Saturn have a surface? No, you just keep falling and falling and falling and not in a good way. And what happens if you add more mass to Jupiter? What? Does it? I guess we'll find out. Okay, so before you leave, we are going to have an open house tonight. If you've never been to the observatory, it's free. You can bring anyone you want, but please carpool if you can. So we limit, I mean, there's like a limited number of parking spots up there, more than 50 cars up there. Gets kind of sketchy. Okay, we'll be looking at the moon, galaxies. I tried to look for the mini moon last night. I was not successful. I know, I cried too. Okay. Questions, comments, concerns? Yeah. Yeah, if you have the lecture tutorials done, go ahead and bring them up here. And then if you want to bring any homework here, and if you're missing your check-in, here. $7:15. All right. Oh, I. I'm having a break. Turn in. Okay, that's gonna be great.
Sorry, go ahead.
Yeah.
And also, check-in.
Okay.
So I'll put that in as well as you.
But I do have an office. So next to my office is the business office and there's a.
Okay.
Anything you want to, you can leave it.
Okay, so I can turn it on.
Yeah. I mean, I won't see it until Tuesday. So it doesn't matter. What did I say?
That, just to give us the grade, says.
Oh yeah, give yourself a grade and then bring it back so I can do it.
Just call everyone.
Well, not forever.
Oh.
Diana Morale. Yeah. Until you can find a book, or if you. Here, I'm just gonna write that down. Okay. Oh, those are on Canvas.
Okay,
So in module, you'll see lecture tours you can download it.
okay, and then I have almost everything done. You want me to just bring it to you on Tuesday or see what everything looks?
I mean, I won't see it till Tuesday, so.
Oh, okay, regardless. Thank you.
If you're what? Turning in? Okay. I tell people not to.
My mom's older, I like go.
You know, and that's in particular why. So like, you know, we try to keep the space up there, but. People up there.
What do you enter for that action?
What?
What do you enter for that action? You wanted to know.
It's called Badger. It's normally closed, but I have keys.
Oh.
It's fine. Open.
Really?
Oh, there's lots of people have keys. Sometimes people call me and they're like, is it supposed to be open? I'm like, I don't know. I hope so.
So like, where is it at?
If you put it into Google, it'll actually, it's better than I am.
Okay.
Yeah.
Thank you.
My name was Helen.
Yeah.
I turned it.
I know, but what did I say? Oh.
This is
the second person to happen to. Okay.
Me too.
Third?
Yeah.
No, okay, this is fine. What happened this?
I turned it in.
When you don't have it?
I don't have it yet.
Okay, I should have brought my notepad today. I'm stupid. It's gonna be such a weird recording. Good thing no one watches these.